So this is on the heels of talking about sizes of atoms and sizes of ions. Remember, we decided that anytime an atom like a metal gives up an electron, it gets smaller. So cations are always smaller than their parent atom. And then something picks up electrons, like those nonmetals, they become larger. So anions are larger than their parent atom. So kind of in that idea, we're going to talk about the energy associated with that transfer of electrons, okay? We're going to start with the energy associated with kicking off an electron. It's called ionization energy, affectionately called IE, okay? So you're going to see some energies here in a minute, and they are always in terms of kilojoules per mole of electrons that are kicked off, okay? So they're always it's always an endothermic process. If you want to take an atom or an ion, you still looking for it?
Yeah.
What page is it on?
It's on the 6th page of part 5. Okay.
Yeah, so it's before that.
Okay.
I
This
think.
is part. Oh, you know.
Yeah. Yep. Yay. So we said that actually metals tend to want to lose electrons, okay, to form cations. So actually we're going to see that with regard to the ionization energy. But so in general, if you have low ionization energy, then that means it's pretty easy to kick off an electron. And we're going to see, though, there's not just the one ionization energy. If you take a cation and kick off another electron, that's the second ionization energy. If you kick off a third electron, that's the third ionization energy for that species, okay? So in general, metals have kind of low ionization energies. It's kind of easy to kick off an electron, okay? Non-metals, if you try to take like fluorine, like one of the halogens, and kick off an electron, you're like, it doesn't want to kick off an electron. It would much rather take in actually one more electron, those 7A elements. So there is this trend just for the group A elements, okay? So ionization energy increases if you get closer to the nonmetals, okay? And ionization energy increases up the group, okay? So I think we've seen this trend a few times. So this is just for the group A elements, and there are some exceptions. So for instance, if we pick on, this is, let's see, this is, yeah, okay, good. This is 1A elements, and this is how big they are, okay? So notice lithium's a lot smaller than cesium, makes sense. With regard to kicking off the first electron, okay, it is a lot harder to kick off that one electron of lithium, and it's a lot easier to kick off that one electron of cesium. Ionization energy right there. It kind of makes sense because if you figure by the time you get to cesium with, oh my gosh, how many electrons? With 55 electrons, okay? You know, kicking off one electron, it's a lot larger atom. It's a lot easier to kick off that last electron, or the outside electron. So this is ionization energy by period. So you see it kind of goes along and ends with the rare gas. Okay, you're like, how hard is it to kick off an electron of helium? Neon, argon. Well, pretty hard. Okay, so those are your rare gases. Okay, and in general, it gets harder to kick off an electron the closer you get to the rare gas. Like I said, there are some kind of exceptions. This, again, is just kind of showing you the picture of ionization energy. This is potassium. Yeah. So this is period 2, period 3, period 4, going across just the group A elements. So this hopefully looks familiar. Remember, your unit exam on Thursday is going to have a lot of things, including how do we configure electrons. The other thing your unit exam is going to have, and I warned you, is going to have nomenclature. That's the other reason I kind of wanted to get your homework back to you. Okay, you will nomenclature just for ionic compounds. But anyway, this is how each arrow represents an electron, and this is the box and arrow notation of how the electrons are configured. This is just one period. This is just period 2, lithium through just oxygen here. So the point here is it's a lot easier for lithium, we said, to kick off that electron than it is for oxygen, say, to kick off one of these electron in these degenerate, three degenerate orbitals up to P. I think that's all that is. So ionization energy increases as you go. That's going across the period. All right. So I mentioned there's the ionization energy to take off the first electron, okay? And then there's the ionization energy to take off the second electron, okay? And then there's just the ionization energy to take off the third electron, etc. So actually I brought in the good old handy-dandy CRC handbook, which before internet, now I went to school, there was just barely internet, okay? But you can find all sorts of physical properties, including ionization energy, on the internet. But before internet, there was the CRC. And it makes a great thing to hit students over the head with. No kidding. I'm just almost serious about that. So, like, one of these tabs is all just a table about ionization energy. Oh, there it is. I marked it. Ionization energies. Now, there's some, I know the pink actually is a candle that bled onto my CRC. It smells good. But alternatively, so all sorts of physical constants in there. I was going to show you this. Oops, I guess I need to have internet. You know that it's called P table, that online periodic table that I kind of put a link up to a while back. That has ionization energies. By the way, check this out. It's like working. I stayed late, like after class last Monday, because I'm like, oh, we got to get this so it doesn't, like, you know. And I could not get it, but then today it's working. Yes. So here's that table I was talking about. The dynamic periodic table. So remember that this actually, this is on my iPad too. There's apps, I bet it's for your Android. Basically, you need to have internet connection, but then you have this, it replaces the CRC basically, okay? So by default, it comes up, I think it might be this Wikipedia one, okay? It just comes up like that. But what I did is if you click on properties of the elements, of course, and I don't know how well you can see it, but one of the properties is the ionization. Okay, so I clicked on that radial dial. Now it's already kind of, you see the slider right here? Okay, if I put that slider clear over there, all of these then, it's giving the first ionization energy. So for instance, if I want to click on potassium, K, it will show me the first ionization energy for potassium. Okay, so, oh my gosh, that is so small. I got 418.8 kilojoules per mole. Okay, so if I go ahead and slide this up, okay, now it's highlighted on potassium, okay, so the fourth ionization energy is 5,877 kilojoules per mole. I just think that's so cool. Okay, all sorts of things. Now eventually, like potassium, well, let's pick, if I go up high enough, so that actually is the, I think what I say, the fourth ionization, fifth ionization. If I go up high enough, click this, go up to like the, 13th ionization, you're like, that's like taking off the 13th electron. Look at all that energy for that. I just think that is so cool. It's the little things. But this is a good website for all sorts of things. We've been talking about how electrons are configured. There you go. You want to see the answers to all the problems you'll see on your test? You could pick on chromium. Let's see, how are the electrons of chromium configured? Man, it's like, yeah, oh, okay. Yeah, I guess you can see the tiny arrows in this box and arrow notation. So this is the answer to some of your homework. Chromium. Of course, that's our first exception to the lowest level, but I just think that is so cool. Oh, here it is, too. You don't want to squint. Here's how those 24 electrons around a chromium atom are configured. Yep, I'm just saying. Okay. All right. Back to this. Okay, yeah, if you want to, if you're curious in that, if you just Google P table, it'll take you, it's like ptable.com or something, where we were. Okay, and again, there's apps for your Android, apps for your whatever. So it gets harder and harder to kick off an electron. So that's why it says the first ionization energy is the least for a given species. The second one, you got to put more energy into it, etc. Third is even greater. Okay. And I have some videos, I'm picking on magnesium to kind of make the point with regard to kicking off extra electrons. Okay. So magnesium actually has 12 electrons. These are how the 12 electrons are configured around magnesium. We kind of peter out with 2 electrons in the 3s subshell. Remember, magnesium is a 2A element. It forms a +2 cation. The things that get kicked off are those 2 electrons right there, normally. But let's just kind of look, hopefully, stepwise, what happens with magnesium. To kind of summarize the little videos we saw, the first one took 738 kilojoules per mole of electrons that are kicked off. The first one did. The second one was 1451 kilojoules. The last one was 7,733 kilojoules. So hopefully you guys would say something about it already had a rare gas configuration by the time you went to kick off the third electron. Okay, does that make sense? Why the big jump there? And actually we're going to see that big jump here in a minute on tables of other elements.
So why that big jump? Why does it have that ridiculous jump?
Okay, actually this is showing you the big jump right here. The little pink line there is showing you where that element already has a rare gas configuration. So with the Mg+2 rare gas configuration, you can make it go to Mg+3, okay, but it doesn't want to do that. With aluminum, aluminum is a group 3A metal, aluminum. So we know it's going to form a +3 cation, kick off those 3 valence electrons. But notice that when you try to make it aluminum +4, okay, it's not happening. Now, with silicon and phosphorus and sulfur and chlorine and argon, are you recognizing we're kind of getting into what the nonmetals? And nonmetals don't want to kick off electrons. Okay, so they're just generally higher. Okay, so which brings us to this idea. Okay, kind of the opposite yin and yang of ionization energy is electron affinity. I always think of like I have an affinity for chocolate. It just means I really like chocolate. So electron affinity is basically something who really likes electrons. She can talk louder than me. Okay. So but what we're going to see this is not always endothermic. Sometimes this is exothermic. Sometimes energy is released when you add electrons to something. Ionization energy, always got to add energy to make it happen. Okay? So actually, I'm counting on you remembering the whole, do you remember we said delta H's are negative if energy is released? Good. Okay. Delta H's are negative if energy is released. Same thing. Your electron affinity energy can be negative if energy is released. Okay? If the energy change creates something that's more stable, if adding electrons creates something that's more stable than what you started with, it's going to be negative. Okay? If adding electrons actually creates something that's less stable than what you started with, okay, then it's going to require energy. Okay, energy is going to be required, and your electron affinity is going to be positive. Okay? So, and it's just consistent with what we've talked about before. And here in your, when I show you kind of hints for your homework, what I do is I actually make it, hope this works for you, because I think it's on my notes too. But the energy associated with enthalpy change of adding electrons, okay, delta HEA, okay, the energy associated with adding electrons, electron affinity. And actually, I think also in your homework, if you're stripping away electrons, I call it this, delta H, i.e. So the reason I kind of did the whole negative negative electron affinities are actually something that where energy is released, okay, it's a more favorable situation, is because here, when I say electron affinity increases, okay, actually, when I say electron affinity increases, it's actually potentially becoming more negative. Electron affinity, the want of an atom to have more electrons increases. Now, does that mean a negative delta H? Yes. So this is where, I don't know how you want to resolve this in your own mind, okay? The affinity increases, but the value of the electron affinity becomes more negative. Okay, less positive, direct. But we do see kind of the same, not so surprising maybe, okay, the affinity, electron affinity increases as you get closer to the nonmetals, okay? Nonmetals want to form anions. They want to get electrons added onto them, okay? Electron affinity increases as you go up the same group. Okay, because the higher the electron affinity, which quite frankly could mean a negative value, the higher the affinity, I'll emphasize the word affinity, the more negative the electron affinity value, okay, the easier it is to acquire electrons. I think I've got some values here to kind of show you for electron affinities. Okay, so not so surprising then. Who has an affinity for electrons? Well, it's not the metals because they want to give off electrons. Okay, so it's the nonmetals. You'll have your higher electron affinity values, basically your more negative electron affinity. Yeah. So I think this is like a repeat slide, isn't it? Okay. And Madison's leaving us. She promises to come back Wednesday, I think. Okay. All right, so this is what I've been talking about. Okay, we kind of have a tipping point of electron affinity is equal to 0. That means it's kind of a net wash. It means you don't have to work to add electrons, and energy is not released when you add electrons. Okay? But if it really has an affinity, it's kind of like getting charged up with chocolate. It's going to release energy when you add electrons. Otherwise, you're going to have to work to make electrons be added. So here we go. Remember, the negative means actually energy is released. And I can't, like I see, nitrogen, see some kind of interesting things going on with nitrogen and phosphorus, and I can't entirely explain all that. But these all look exothermic. Well, kind of a wash with beryllium and magnesium, except for nitrogen. Okay. So down there at the bottom is kind of, if you, like on a homework, need to show the process of adding electrons and kind of the energy associated with it, this is kind of what that would look like. You take something, it could be a neutral atom or something that's charged, and you add an electron to it. Okay, you end up with something that has one extra negative charge. Okay, then over here actually, you would write the delta HEA, kind of how that goes. We'd have a delta H electron affinity is equal to whatever, and those are the values in units of kilojoules of energy per mole of electron that's added. This is just kind of looking at electron affinities. I definitely see exceptions there. And this is just to kind of show you, again, the box and arrow notation for the elements in period 2. And it looks like it would be much easier to just pull up and park an extra electron or two here, okay, than it would be to start parking an electron here. You're much closer to the rare gas down there. Here, it's easier to lose that electron, and that's what we've been talking about. We said lithium forms a +1, beryllium forms a +2, boron, that's a non-metal because it's on top of the Jag. I don't think we didn't really say what it forms. But starting with oxygen, we said it forms a -2, nitrogen forms a -3. And yeah, boron and carbon, I don't know, they could go either way. So with regard to, this is going across the period 2, notice that electron affinity increases as you get closer to the oxygen. I almost said closer to the chocolate. So I have this video queued. Take a look at the hints for these or what these are. Again, the answers are under talk sharing. So I'm not saying you have to go out there, but it's a thought. So these will be due when you come to take your test.
On Thursday?
No, these will be due on Wednesday. Sorry. Thanks. This one. Okay. So, like the first one, I would find these 5 elements on the periodic table and just eyeball them with regard to ionization energy, rank them in order of increasing ionization energy. Nothing tricky there. You don't have to look them up. Okay? Just use the periodic table. For the next one, are there any atoms for which the second ionization energy will be less than the first ionization energy? And I doubt it. I can't think of any. So just put some blah, blah, blah with that. But, you know, I just think it always gets harder. To me, did you see how I loved how the animation showed it getting smaller? I mean, dang, it's harder to rip off an electron when it's smaller like that, too. For the next one, some electron affinities are negative quantities, some are 0 or positive. Why wouldn't this also be the case with ionization energy? And it's kind of what I said in lecture. It always requires energy to remove an electron. That's ionization energy. And species actually can go either way with regard to adding electrons. They can be more stable, and then you get a negative electron affinity, or positive, and it does require energy. The last one, this is what took me a little bit while, because this one and then the other two, actually, I wrote little kind of equations. So the last one says, we didn't do anything quantitative at all yet. You guys have not had to use your calculators at all, and you won't need it for your unit exam. But this is a place where you could use your calculator. Basically, it says, we're going to take neutral sodium in its gaseous state. We're going to zap it with energy, and actually what I should have done was say plus energy here. So just say plus energy. And then what we're going to get is the sodium +1 cation, which makes sense, and an electron, right? They went ahead and gave you the ionization energy for the first ionization energy for sodium is 495.8 kilojoules per mole of electron that's kicked off. Okay? The problem goes on and tells you how much energy is required to go ahead and ionize 1.00 milligrams of sodium. So my hint was to use the molar mass of sodium. Okay, this will be good refresher. Use the molar mass of sodium to go to moles of sodium. Okay, and then recognize that for every 1 mole of sodium, you require 1 mole of electrons to go to moles of electrons. That's just going to be a 1-to-1 relationship. And then actually you can use this energy per mole of electron to get to energy. That was my hint. So the other two look like this. Now this is my first semester to kind of go through 27 and 28 as they're assigned. In this one, they say basically you're going to make Br-1, the bromide ion, from Br2. Okay, but Br2 is a molecule, so the first thing you got to do with Br2 is break it. Okay, break that covalent bond. It's a diatomic element. to make individual neutral bromine atoms. So basically, and this is kind of similar with the next one too, if you think of the overall process, the overall thing you're trying to do is at the top, the reaction of interest. What are you trying to do? Take a molecule of Br2, add a couple of electrons, and get bromide ions out of it. Okay? That's what you're trying to do. It actually happens stepwise. It happens, the first step happens, and then the next step happens. Okay, so if you kind of think of that. Now notice when I say add, I think you're going to have to do some manipulating with like scaling them up, because like instead of 1 electron, it's 2 electrons. Okay, that sort of thing. But in general, you add. Remember, you can get the electron affinity for step number 2. You can get that value from your textbook. That's in the little box, one of the little boxes we saw. And then 28 is kind of similar. In this case, it's kind of fun. We know magnesium forms a cation and fluorine forms an anion. So the question up here is, okay, what if you go ahead and take magnesium, 1 mole of magnesium atoms, and 2 moles of fluorine atoms, okay, and go ahead and make the cation and the anion? How much energy is going to be involved there, okay? So again, if you break it up stepwise, now notice I got in a hurry, and again, I would actually have these 2 steps right here. You take regular magnesium plus energy, and you get your Mg plus 1, okay, plus 1 electron. Then you take your Mg plus 1 plus energy, you get your Mg plus 2 and 1 electron. Probably that's how it should be broken out. And then the fluorine, well, fluorine is going to pick up electrons, so actually you're going to use the value in your textbook for the electron affinity for fluorine picking up an electron. You're going to have to scale this one up, though, aren't you? Because it's not just 1, it's actually 2 there. So anyway, in that kind of mess, I've kind of given you hints how you actually can have, I believe, 3 equations to get this overall reaction of interest. So Hess's law says if you can have little baby equations that add up to the overall equation of interest, then their enthalpies are additive, and that's exactly what you're doing. All right. Good?